So I hope everybody can see this. And let me go ahead and have the chat box up because I like to see interaction. If you have comments, if you have certain questions, I like to make this interactive. So if you have questions, concerns, things like that, then you can go ahead and type in the chat box, and I like to address them as it comes along. So, this is your opportunity to ask those questions that you've been wondering about, not only COVID-19, but anything related to COVID-19, because this is something is still a new condition, something that we're still trying to learn and understand. So one of the disclaimers, actually two disclaimers that I like to start off with. Number one, a lot of these things may look like medical advice to you, but this does not replace medical advice that I'm giving you, even though I do have an MD and I have the knowledge, but what I say in this lecture does not replace any personal medical advice. If for that, you would need to consult your personal physician. And the second thing that I love to start off with, when I'm explaining about COVID-19 to students, is the fact that a lot of this knowledge is evolving. So something I say today may be true today, but tomorrow scientists in United Kingdom or somewhere else, the reason I bring up United Kingdom is a lot of the original research came from there. They might say something completely contradictory to what I just said because they just discovered something new. So there's a lot of different components here that is factual currently, but may evolve. So be on the lookout. Take a look at articles. Keep looking at articles and see what it says. That's the only way to make sure that you're keeping tabs of what is current. Okay. So with that said, what will we be going over today? Well, I want you to get a really, a basic understanding of coronavirus disease transmission. So one of the myths that is out there is, how this thing spreads and why wear masks, who does it protect, things like that. A lot of people, even reporters I've seen this, actually make this mistake. They think that a mask is worn to protect yourself, But the main reason that a mask is worn is actually to protect other people. So when you are projecting, when you're, if some of you sing maybe, one of the first studies that came out, of course, one of them was in the restaurant in China, but also in Washington State, there was this choir practice, and people were in church choir and they were singing, and one person who was a super spreader spread it to about 50 to 60% of the choir. So you'll see these super spreader events, and of course there was no mask being worn, and certain places where many people contract the virus from certain events. So you'll hear me, what I like to do is I also like to give you stories and examples. Facts are great, percentages are great, but there is nothing that also replaces real life stories where people, just like you and me, contracted the virus. And some of them did not have such positive outcomes. You might have heard about the 9-year-old that recently passed. That's also another tragic situation. And so, Sally, thanks for that question. So, what basically you're asking what determines one person will be a super spreader and another person won't be? And there, that's a really good research question. The answer to which is not quite known yet. The problem is there's so many unknowns, and that's one of them. There might be, in fact, it might have to do it might not necessarily have to do with people, but in a certain circumstance, in a situation, there might be super spreader events. But the one story that I like to tell when it comes to super spreaders is I like to go into history too. So Mary Malone was has any one of you, and you can kind of say yes or no, however you want to. Maybe you can type it. Has anybody heard of Typhoid Mary? Yeah. Okay. Okay. Great. So you're familiar with that story. Okay. So that situation, if you think about it, so Mary was for those of you that may not know, typhoid fever was something of a common occurrence about 100 years ago, and so it wasn't in that situation necessarily the fact that she was a super spreader, but the fact that she was a carrier, she didn't necessarily get too sick, and she was in a position where she could be spreading this to a lot of people. And now in the case of typhoid, that is actually a bacteria, but regardless, she was an asymptomatic carrier. And I'm going to be talking a lot about asymptomatic carriers, so I'm not going to talk about that too much. But the fact that she was a cook and she was preparing food meant that she was in a position where she could be a super spreader. So it's not only the fact that maybe certain people are, but it's the types of activities that they are engaged in may also have to do with why certain people are, quote, super spreaders. So there's a lot of things going on there, but if you haven't, if you're not too familiar with that story, or if you haven't read that story in a while, I encourage you to go ahead and do so, because that one incident actually infected 53 people, and in fact, 3 people died from that. So I think that's one of those stories we can learn from. And I'll also be using 1918, the Spanish influenza, as a comparison for what is going on today, in order to better understand what this is. Okay, so so again, we're gonna create kind of a foundation through a basic definition of what each of these concepts mean. Okay, so I like this picture because of the fact that it brings home a couple of things with COVID-19. First of all, it's a virus. It has spikes on the virus, and the reason that it's so difficult to understand the behavior, so to speak, the behavior of COVID-19 is because, first of all, you can't see it with a regular microscope. Has anybody ever looked through a microscope? Does anybody have experience doing that in a lab or? Okay, maybe. Okay. So some of you have. So when you have the 4, 10, 40. You have the objectives, the objective lenses, and you have. Let's for instance, okay, so let's, for instance, imagine that you're looking for COVID-19 under a microscope. Well, you look on the 4 objective, nothing. You look at a sputum sample of 10 times objective, nothing. 40, you can't see anything. Let's give an example of, for instance, trichomonas. So in STD lab, of course, you would take a sample and you would look, and you can see trichomonas like right away. There's no questioning that. You can see a lot of different species, Pseudomonas. You can see a lot of bacteria. But now we're talking about virus. These particles are even smaller than the smallest type of particle that you can see. So you have to go to something called an electron microscope to even be able to see anything that is there to see. So you go to this huge microscope, and when I was at the Centers for Disease Control, we actually had one of these electron microscopes that took up a whole room, and we actually had an in-house electron microscope expert that her job was to specifically put in all the images and show you the picture. And so we were looking at, of course, at that time, a bacteria. But these viruses, it takes something of that magnitude, something that powerful to even be able to see. So how does something this small cause that much devastation, right? So it's just, it's mind blowing. So anyway, so this is the blue is a dye that they use to be able to contrast so that you could see this coronavirus, this COVID-19. So I love this picture, and you'll probably be seeing this in other slides because I like to use this as a background so that it's a reminder to all of us that this particle is so tiny and yet, causing so much devastation. On a philosophical level, it's almost humbling. So what do you know about this virus? And I know you've been, frantically looking and reading and collecting information, trying to figure out how to stay safe, how to protect your family. So I know there's a lot of things. So share with us like a fact. And if you want to, get on your speaker, if you feel like talking, or if you want to type it out, just give us one interesting fact. I mean, it doesn't have to be an interesting fact, any fact. It doesn't even have to be a true fact. It can be something that you think is true, and maybe it's not. What I'm saying is there's no wrong answers. Okay. So Burke, and also I wanted to mention, if there's a name that you would like to be called, you can change your name. So I usually read the name that shows up on the chat box. But if Burke, if you would like to be called that, then I'll call you. And okay, good. So yeah, it can be passed from a person without symptoms. So that's definitely a really interesting fact. Let's see. So Sierra is saying, and excuse me if I'm mispronouncing anybody's name. It affects the lungs. Yeah, that's correct, Lorelei. It can cause blood clots. But yes, we will be going over that on Thursday as to why. It's airborne, Tillman. Okay, yeah, that's good. And then it can linger and reoccur. Okay, CDOD, that's good. And I think recurring is when you mean reoccur, are you meaning that you can fight off the infection, recover from it, and then get the infection again 3 months later? I don't know if that's what you were referring to. That's correct, but I wanted to bring that to your attention. That's actually a very recent sort of finding that is coming out of King's College. There was a separate study that was done in California that is showing that if after 3 months, you can actually, your immune response it starts to dwindle, and then you can get COVID-19 again. Not only that, if you're if you get mild symptoms, or maybe are asymptomatic, didn't really get it that much, then the immune response actually it actually clears out of your system even sooner, so you can contract COVID-19 even sooner than 90 days. Okay, so I wanted to kind of bring that up since this is newer information, and you'll see me also give you updated information as we go along. Okay, so Rachel said protein is the reason it's able to attach to humans, and I'm going to go over that in great detail. So good. Okay, Hannah, it can make you lose your taste and smell, correct? And it could also give you an altered sense of smell. It can stay on surfaces for up to 3 days. It can, right? It's, of course, these are upper limits. A lot of people say, it starts to clear up sooner, but yeah, up to 3 days, correct. Okay, how much, Chester, how much we don't know is frightening. That is also another good fact. It is frightening. Carol, some people die from it and some don't, correct, yeah. And how, the question is, how do you determine? I mean, we have some facts like comorbidities, things like that make people more susceptible for obvious reasons. And I'll go into a little bit more detail as to why comorbidities. I'll discuss about that today and Thursday. Different people in same family can present different symptoms, correct, yeah. It is an RNA-based virus. Good. We're getting into a little bit more technical material, but that's great. That's so just to give you, and I'm not going to go into. I took a whole 6 months of virology, and actually probably more, a lot of virology. There's DNA viruses, there's RNA viruses, and different characteristics depending on the type of viruses. But I would have to go through what DNA is, RNA is, and a lot of different things, and it's beyond the scope of this course. But yeah, that's a good fact. Okay, so CEDAW. Okay, Herbert, it sticks to stainless steel for 2 days. Interesting. Okay. Yeah, so different surfaces have different time spans that it sticks, and great. Okay, so it can stay alive and viable on indoor surfaces for long periods of time. It can, yeah. Dylan said that. Good. Okay. And Kayla, it affects those with compromised systems, unfortunately, worse. Roz said asymptomatic situation can be misleading. Correct. That is what makes this so much more dangerous. And I gave you the example of Typhoid Mary from history, but there's so many more examples in current modern day of looking into that. So, I start to make lists. Of course, I'm a researcher, scientist. So I start to, when I look at phenomena that have not been observed before, I like to make lists and have people with certain symptoms in certain groups so that I can keep track of how this is evolving. And if you're one of those people that likes to make lists, that might be something that might be a way to keep track. Okay, so Alana, it affects people differently, correct? Yeah. Okay, let me see. And then Melanie. So Melanie, you have a question here. You're asking if it's so harmful and so harmful, if it's so small and harmful, how is it possible that a pregnant woman has it but when she gives birth, the baby might not have it, and their lungs are not fully ready. Okay, so I think what you're asking here is the fact that, of course, a baby, especially if you have a premature baby, your lungs may not fully develop. That's one of those things that develops last. I mean, heart develops at 4 weeks, so you know, or starts to develop at week 4. But lungs actually are one of the last major organs, you know, to develop. So a lot of times we'll give, you know, prednisone and things like that to hasten that process. But how is it that a pregnant woman might be positive and they might not pass it on to the baby? So the placental barrier is actually a very strong barrier, a filtration system, which allows for some protection of the baby from mother's, you know, infections. Now, I'm going to say this, but then I'm also going to say another thing. There have been some reports. Now, this is kind of getting to the point where we're reaching a gray area, and I'm also kind of alerting you about that. But there have been some instances where there's possible transmission from mother to child. So initially we were thinking that is not possible, but there have been potential situations. But we're still going to have, you know, the verdict is out on that, and we're still going to have to have confirmation on that fact. But yeah, I think it goes back to that one statement that was made by Chester, which can't be further from the truth, is that how much we don't know is frightening. I think that's a quotable quote. But yeah, that's a good point. Okay. So you know, moving along, I think we had a really good discussion on this. Dylan said, "Is it safe to say that it's best to keep our options malleable?" Yeah, that's an interesting way to put it. Yeah, exactly. Yeah. Okay, opinions. Yeah, opinions malleable. Yeah. This more than ever, and this is why you need skilled individuals giving you lectures on this, not somebody, you know, that you know, learned everything in a day. I mean, this has been similar things has been my life's learning. I've been learning about this. So this is why people that know a lot about different areas need to be teaching you, because of the fact that everything is so malleable. Okay. So let me get rid of this. Sure why this underline came on here. I don't know if you see it on your end, but there's like a red mark. I just try to ignore that. I'm not really sure why it's on here. Anyway, okay, so I think it's from the annotation tool that is on here. Let me clear that. Clear all drawings. Okay, better. So out of these, you know, and this is kind of more here for historical reasons, more so than anything. But you know, the initial 3 symptoms. Okay, I'm not really saying that one of these symptoms cannot take place ever, but the 3 best symptoms, or the 3 most valid symptoms, are what out of this? And I want you to pay attention to this because of the fact that you might see this again. And if you could just type on the chat box like Lorelei did. Yeah, good. Good. Okay. Okay. So all of you are on board with this, and yeah, see, immediately recognize what these are. Now, like cough, fever, and shortness of breath is the right answer. Okay, so now can it affect your eyes? Can it give you blurred vision? Absolutely. And so the fact of the matter is, in fact, that, and I'm going to give you a little bit of a sneak peek into Thursday. ACE receptors are something that are present in your eyes. So the eyes are a potential point of entry for COVID-19, not only through the nose. And so, it's one of those things that there's so much that is potentially possible from this virus. Okay, but those were the original three. And now I'm going to also give you this fact that if you go back to the CDC website now, there are a lot more symptoms. In fact, GI disturbances, and what I mean by GI disturbances is diarrhea is one of the symptoms that has been incorporated into the symptoms. So I urge you to go to the CDC website and look at all of the different symptoms that is possible from this. And again, it's very important for you to know the list of symptoms, kind of have a good working knowledge. If you know cough, fever, shortness of breath, that's good. But just keep in mind that there are other symptoms, one of which can be gastrointestinal disturbances, specifically diarrhea. Okay. So now we're going to go over some basics here with viruses. And, there might be certain facts that you might already know about viruses. I might have already kind of touch base on this, but the fact of the matter is there are so many different components. There's so many different concepts here. So you might know a little bit about a certain aspect. You might know a little bit of another aspect, but what I'm going to try to do is give you these smaller pieces and then piece that puzzle together to indicate to you, why does a virus get you sick? Why does it make you feel sick? And go over that. Okay. So again, I already explained to you what a virus is, and as I indicated, of course, it could be DNA or RNA, and basically a virus acts as a blueprint for basically the genetic code acts as a blueprint for the virus to make more of itself. So, okay, so I'd like to go even further back and kind of start at the foundation here in explaining viruses. When I first, took my very first class way back when in biology, one of the things that struck me was the fact that from a strictly biological sense, a virus is not considered living. And why do I say that? Well, in order for something to be classified as living, they have to be able to independently reproduce. And a virus is incapable of doing so. They actually need are dependent on a host to be able to reproduce and make more of itself. So it not only needs our DNA, it requires our machinery. So what I mean by that is it requires a nucleus, and so yeah, so a parasite does require another host in order to survive, in order to eat. I'm responding to Sidav's question about making it a parasite. So it does, a parasite requires something to survive, a host to survive, but a virus specifically requires, and this is into semantics and definitions and things like that, but the point being is that, you know, there is no other organism that is so dependent on a host, so exclusively dependent on a host for survival and reproduction. So how does it do so? And I'm going to kind of generically go over this before I go over this in greater detail. But it actually has to go in and invade the nucleus and hijack the whole system in order to make more of itself. So let me, at this point, make this drawing here and show you what happens. Okay, this is too, there we go, okay. This is the right tool. So typically you think of a virus and you think of kind of a hexagon pattern. The head, there's a nucleocapsid, and then there's all these tails, and that's the typical structure of any virus. This is not just COVID-19 or SARS-CoV-2. It's any sort of virus looks like this, and then there is this host cell, and you know, we spend a lot of time going over the structure of a cell. So I'm not going to go over too much about the structure of a cell. I'm going to tell you that the DNA and DNA reproduction, everything takes place in here in something called the nucleus. And that text box is way too big, but here, let me shrink it down. So there's the nucleus, and of course, here is the viral particle. And you know, I'm not going to expect you to draw it in a quiz or in anything of that nature. This is for your personal knowledge. So there's the virus and there's the nucleus. And of course, the size is not of a virus is nowhere near what I have drawn it. This is just for illustration purposes only. If I were to actually draw to scale, you wouldn't be able to see it. So the virus on its own is defenseless. It actually is incapable of reproduction, can't do anything. Now, the recipe for disaster is this: once this virus goes and actually starts invading the human host, and imagine this is like a respiratory cell, a cell in your lungs. It enters through, there's actually receptors in our cell, which the virus, of course, has, you know, it's through mutations, it has created these proteins which interact with the ACE receptor. And I'm going to go over the ACE receptor in a lot more detail. So I just want you to know about the ACE receptor at this point. So it's going to go in through the ACE receptor, interact, and then once it breaks this barrier, it can't just enter. It has to enter through that particular receptor, and that is the only way that a virus can enter. So if we completely long enough to spread, okay, I'm going to go over that. So if we eliminated these ACE receptors completely, or blocked them somehow, or did something, then there would be no way that this virus could even enter, because it can't just, this virus is not capable of entering through here, it can't enter through there. Only way it can enter it through there is through ACE receptors. So it goes in, then goes into, once it's in the cell, it makes its way into the last, goes to the last defense, penetrates through the last defense in the nucleus, goes into that genetic material, hijacks that genetic material, and it's like a computer virus. It takes over and starts making more and more of its own self. So initially, when you're asymptomatic, or you have little mild symptoms, a couple of cells have made viral particles. No big deal. You don't really see anything or feel anything. But then as this continues, as this process continues, and more of these normal human cells are actually being programmed into turning more and more viral particles. And I'm just going to draw these things here. There's more and more viral particles. Then all of the energy that we are using to try to fight this infection off instead is going to make more and more viral particles. So it literally converts our cells and transforms them into virus-making factories, virus-making machinery. So it's at this point hijacked our system, and now we're getting more and more symptoms, to the point that, and what makes the difference between some people going, in one direction and another. I'll give you some sense of that, on Thursday, but this is kind of the introduction. This is the foundation of how the virus comes in and starts to take over. So the new virus then will spread through your body and out into the environment. So the ideal virus, and this is something we talked about. I learned this a long time ago. The ideal virus is not the virus that actually completely kills the host. The ideal virus is the virus that makes you sick enough so that it's able to transmit to more individuals, so that more viral particles can be made. So that's what makes that makes for a very dangerous viral particle. The one that can, kills some individuals, some hosts, but not all. Okay, so let's go to the next slide. So because these resources are being diverted from making more, giving us more energy and providing nourishment for us, to just making viral particle after viral particle after viral particle, because it's being diverted, that's the sickness we start feeling. And of course, organs are starting to suffer. Lungs, the heart. There's quite a few organ systems, as you'll see on Thursday, that this just starts to affect. And I'll explain to you the major organs that are being affected. I'll explain to you why you get the symptoms and why you see the things that you do in the organ systems that are within your body. So the human body activates the immune system to fight off the virus. Of course, that's there, and we can't forget that. But because of the fact that, you know, there are a lot of first responders. Of course, macrophages are first responders in our body, but also you know, a lot of the T cells, they're coming in and activating more inflammatory markers. A lot of that, creating that defense system actually takes away from energy that we have for to run other body systems. So there's two things, two major points here. One, the diversion of resources in order to make more of the viral particle, that's making us sick. And two, the diversion of resources from other body systems into maintaining our immune system to fight this disease, that's making us sick too. So there's two things. So this is where all of these concepts that I just taught you and showed you through these pictures, they all come together, and then you understand what exactly is going on. And this is the surface where we'll delve into this deeper in order to understand this better. Okay. Okay, so let me clear all drawings so that, you know, this is not getting distracting. But you know, this is, again, getting into what happens when someone is exposed to the virus and how does someone get rid of a virus. So, you know, we're trying to figure out what specifically is, it's kind of like a trial and error where the body tries one algorithm, tries to figure out if it works, and then it's not necessarily completely efficient, but it's just try one thing. If it doesn't work, try another thing. Doesn't work, and you know, usually with all the existing viruses that we have, of course, we get exposed to many types of rhinoviruses. There are 200 different types of rhinoviruses, and there's a reason that I'm bringing this up right now, because as we go into fall, this is a major concern. So there are 200 different rhinoviruses. Rhinoviruses cause mainly the common cold. Not only that, you have a completely separate virus called the influenza virus. It has nothing to do with the coronavirus. It's a completely different family of viruses. Our body's exposed to that. Every year we get exposed. So even though they mutate a little bit, so there's something called antigenic drift, antigenic shift. Some of you might have heard it. Not really important in this context, but the flu goes through small mutations every year. So that's why you need to get the flu vaccine every year in order to protect yourself from the virus. So in the fall, and especially going into winter, we have all of these different viruses that are, roughly speaking, giving you similar symptoms. So those viruses, for the most part, if you don't have other conditions, you have memory cells. Your body kind of knows what type of immune response to mount, and then be able to take it down, be able to attack. When it comes to a novel coronavirus, and that's why the novel part of this virus name is so important. When you have a novel coronavirus, your body has not been primed. Your body doesn't know, the immune system doesn't know how to respond to something like this. So that's what makes the difference between one type of virus and another. So the human body is trying to still figure out, how to fight it. Now, why did I bring up, all of these different viruses that look like COVID-19? Why is that so important going into fall and winter? Can anybody tell me? Can anybody give me an answer to that? Right, right. So not right, and that these are all good points. There's similarities. You can have them simultaneously. Um, so when you have symptoms that are similar that imitate another virus, then you actually don't know um, if you have one or the other. So that's why more testing will be important. More contact tracing will be important because the other part of this, which is so alarming, is the fact that when you do get a test, there's so many instances where it is false negative. And I'm introducing this concept early. This is an epidemiological concept. Epidemiology is one of my many trainings as well. I've spent a lot of time. False negative is a very important concept because what that means is if you get a positive test from COVID-19, okay, so then you know for sure that you do have COVID-19. There might have been scenarios, very small percentage where it was positive, the test was positive, but the person didn't have it. That is not usually the case. But as the testing is still not really developed, is still in the early phases, there's actually a much higher false negative percentage, which means that if your test says no, you don't have COVID-19, doesn't mean that you actually don't have it. Number one, you might be in the early stages, so you might not have a viral load that is detectable by the test yet. Number two, you might have some sort of deviated septum. If the test is still through your nose, and I've actually been a part of this testing process, and it's still the same process where you put a swab up through your nose, and you rotate they count 15 times in each nostril. But if you don't quite have a straight nasal passage, if you have a deviated septum, then you might not get a proper sample. So there's all of these components. There might be operator errors, and there are all of these things that can go wrong in the testing. So no doesn't always mean that you don't have it completely. So we count on contact tracing actually to see if the person was in fact exposed to, and if they're having symptoms, to make sure that that the negative test is actually negative, and that they're not a case of a suspect case of COVID, so to speak. So why I'm bringing all of this up is because I'm trying to make the point that when you have other viruses which imitate the symptoms of COVID-19, then at that point, you no longer know if a negative test is actually negative, and positive because it's negative because you don't have COVID-19 and you have one of the other viruses, or is it negative because it was a false negative? So there are all of these additional unknowns that are introduced when we are going into fall season and winter, which is why, and which is one of the reasons why now, Dr. Fauci and a lot of public health experts are warning about the fall. And I'm going to discuss about the fall a lot more because we're so close to it now. I mean, we're about a month and a half away. And schools reopening, scheduled to be reopening, things like that. These are at the forefront of national discussions. And so I want to make sure that this is current and all of you know the facts going in, and know what is reality and what are things that people are and don't know about. So again, very important. Okay, so if a person has been previously infected or has been vaccinated, their immune system will be primed to remember. Remember, I use that word priming. Your immune system gets trained, or it gets primed react quickly the next time it sees the virus. But again, this is a novel coronavirus, which is why it makes it so much more difficult. So eventually, you know, the immune system, maybe some people's more so than others, eventually their immune system figures it out and understands and realizes how to actually destroy this virus completely. So, you know, it's kind of luck of the draw. Our immune systems, it's a known fact. I mean, immunology, from immunology, I can tell you this, that, you know, we have a lot of variations in our immune system, which makes everything unique. So some people have an overactive immune system, which makes them more susceptible to autoimmune conditions. If you've heard of rheumatoid arthritis or systemic lupus erythematosus or, you know, Sjogren's or a lot of the different autoimmune diseases, it's because, you know, you don't have necessarily an immune system or you have an overactive immune system. And then there's underactive immune systems people have. And then there's a whole gamut that's in between. So that is why, again, there's so many variations of how the virus reacts to some people and how it affects some people and not others, things like that. There are more genetic testing that is being conducted in order to understand these differences. Okay, so here's another question here. After recovering from a virus, can the person get sick again? So I gave you the response to this. So the answer now actually is a little bit more, I would say a little bit more definitive. These things still apply, but the fact of the matter is, and this is studies that have been just recently published. It's not, and actually haven't really even been, and haven't quite gotten into journals yet. But these are separate studies in different countries, different places. One in California, one in the King's College in the United Kingdom, which are very reputable places. UCLA, I'm sure a lot of you have heard of. Scientists and researchers have found that 90 days is how long the immunity stays, and then after which it starts to wane, starts to go away. So it's good to keep that in mind when you're thinking about this. Sally, I like the fact that you brought up the foods or vitamins that can build the immune system. I think a lot of medical doctors dispel the power of eating right, and we a lot of times don't have time when seeing patients to actually go over that fact, but it does remain a fact that in the immune system can be strengthened through these avenues as well. So I wouldn't necessarily go over those here, but I think there's definitely vitamin D, of course, is in a medical context very important for a lot of different areas, and really helps in fighting disease, of course. So I think it's important. So yeah, I think those aspects are important. I personally do take certain supplements, things like that. So yeah, it's something good to keep in mind. I would recommend all of you to do your own research to see what works best for each and every one of you regarding that. I'll go over on Thursday about what parts, what phases in the disease progression does immune suppression work better versus immune modulation, increasing the immune system. Again, not to replace medical advice, but I will show you exactly which phases in the disease process where you need a higher immune system versus where you need to decrease your immune system in order to be better adapted. And this is based on knowledge that we have now. So again, it's for your knowledge that I'll be going over this. Okay. But I think this creates a really good foundation going into Thursday, because I didn't want to throw you into all this pathophysiology, all this medical jargon all at once, because trust me, it can get really confusing very quickly. Okay. So this is kind of the same things. I wanted to include this in order to have it presented in a different way. So because because it's, you know, spread so easily and people don't have immunity, that's a recipe for a disastrous pandemic, and that's what we're seeing here today. Not many people have, very few people have had seen this. Actually, you know, before November or October, whenever the origin was, nobody had seen the virus. So that's why it's such a difficult virus to fight as a population. And 7 billion people at once, directly or indirectly in our globe, being affected is no easy task. You know, it's very challenging. And Brazil, if you have seen, also is seeing numbers that are alarming. The top 5 countries in the world, if you look at the ranking, are experiencing the vast majority, like significant. It's a significant percentage. I think in the U.S. we have about 20 to 25% of all the cases in the world, and we only make up about 5 to 8% of the population, of the world's population. So those are some sobering numbers. So it is, you know, it's an emerging infectious disease. So the disease has recently emerged from the natural host animal in the wild. And I'm saying this for a specific reason, because there still are so many different theories. And coming from a medical perspective and having seen similar scenarios happen time and time again, you know, I have no doubt in my mind. And, you know, there were those papers that were published in Lancet, which demonstrated that, you know, the Wuhan lab theory, it's too outlandish. I mean, it's a theory and it's there, and everything is a theory. But what, as scientists, it's our job to evaluate the evidence. What evidence do we have, and go with what makes most sense given the evidence that is there. And so while that is a possibility, you know, I guess that's a theory, but the most sensible theory is the fact that it transferred over from the wild. And the reasons with deforestation, and if you follow a lot of environmental health, and I do that a lot more now due to the fact of global warming, things like that. If you see a lot of that, you see that more and more diseases are coming out of the wild, because we are encroaching on wildlife territory, on animal territory. So this is the tragic consequence of development, and, you know, all of the different components, overpopulation, and so we have to be more gentle with our environment, you know. And of course, depending on political stance and beliefs, you might have a different opinion, and I respect that as well. Because most people, you know, don't have the immunity, it takes time allowing the virus to replicate and potentially spread. Right, new places also exposed to new bugs, Burke says. Right, and the other part of that is, you know, we have such, we have rapid expansion of globalization that allows for travel to spread the disease from one continent to another instantly almost. And that was the fear. I worked with Ebola, not directly, but indirectly through research. And when you study the phenomena there, a lot of the things that was feared with Ebola would take place. Once there was the first individual that brought the Ebola virus to the United States, there was a fear that this was going to turn into a huge outbreak and might be difficult in the United States, but that fortunately didn't take place with that virus. Okay, so let me go through this, and a lot of this is, information that you've already seen. Of course, just going backwards a little bit, it was first identified in Wuhan, China, but the technical name is not China virus. It's caused by novel coronavirus named SARS-CoV-2. And, there's different strains of coronaviruses that we have seen previously. So you would think that, oh, okay, everything is a coronavirus. So if we defended coronavirus before and we have immunity from that, then of course we have immunity from this one too, but it's a novel type, so that's why it doesn't work. But Middle Eastern Respiratory Syndrome, MERS, you might have heard of that. Of course, SARS, I think all of you probably heard that one. But a virus that reached pandemic proportions, this is something that we really have not seen in recent history. Of course, in 2010, there was one, but right, H1N1. Right. So H1N1, I believe, is not a type of coronavirus per se. And so, but we had seen, coronaviruses in the past. And we had seen pandemics, and H1N1 was a pandemic about 10 years ago, but it did not reach the proportions that this has reached even now. The one that people are starting to compare this to and have been is the pandemic of 1918. And if you go back, the same types of mistakes that were made in terms of people not wanting to wear masks, whole movements created to try to prevent people from, wearing masks, turning it into a debate between individual liberties versus what should be done for the greater good. All these types of things took place in 1918 as well. So approximately 100 years ago, a little bit more. So we saw, if you look at what took place there, and political officials trying to brush this under the rug. When you saw this you saw this with HIV too. Political officials, not wanting this to be at the forefront of what people pay attention to. I mean, after all, it is, of course, human nature to try to think of the positive things and not to pay attention to things that are potentially bringing harm to people, and if you ignore it, it goes away. If you stick your head under the sand, then the problem disappears. This is what we would like to think, but unfortunately, it doesn't go away. So, even North Korea has, initially they had not acknowledged COVID-19, but there's more and more acknowledgement, even countries that were initially resistant to that. Okay, so I think somebody raised their hand. Did you want to speak into the mic or?
No, sorry, that was an accident.
Oh, that's okay. That's okay. Okay, great. At least it was good to hear somebody else's voice than mine. So So that's great. Right. So yeah. So just so H1N1 was it was a type of influenza. So that was the difference. But anyway, okay. So let's go into some. We have about 15 minutes left. So let's go into some of these numbers. And you know, as individuals that are getting trained for contact tracing, it's good to translate these concepts and numbers into what does it really mean. So at the end of the day, I mean, a majority of infections you can say are mild. The problem is we really don't know which individuals will go the mild direction versus the severe 5% in the ICU direction. And you know, death rates have at least in the present moment, you know, even though the case rates are going up, especially in Florida, Texas, California, you know, all of those, a lot of the southern states, Georgia, where I spent a lot of time, and it's tragic to see what's going on there as well. But yeah, with my years in the CDC and all of that, I spent a lot of time there, and it's tragic to see not only what is going on in terms of the disease rate, but also kind of the pushback that is going on in between, you know, mayors versus governors versus the director of the CDC, and all of these things, all of those kind of relationships that need to be there in order to effectively combat COVID-19 is kind of falling apart, and it's tragic. I personally knew one of the, not the current CDC director, but one of the previous ones, and it's usually their job to, you know, have the interest of the public at the forefront, but that's a discussion for, you know, some other day. So transmissibility, R naught, you might have seen this number before. You might have wondered, you probably already looked it up, but R naught is the number of people that one person transmits the disease to, a person who is positive for COVID-19. So, you know, you might think, okay, well, how can you have 2.4 people? You know, what does that even mean? Well, you got to remember, these are calculations. These are numbers that have been, you know, kind of average numbers, things like that. So when you take numbers and put them together and actually average them, they don't come in neat, discrete numbers. There's decimals left over. So anywhere between 2 to 3. That's the best way to put that, you know, what that means. So case fatality rate. That's something that I want you to be able to, you know, kind of practice on. So, you know, out of the number of cases, how many people are actually dying from the disease is the case fatality rate. It's different from mortality rate. Mortality rate and case fatality rate are not. Now, I've seen reporters make this mistake. I believe there was an interview. I don't know if any of you saw this interview between Chris Wallace and the president, but I believe Chris Wallace was, you know, asking about mortality rate and confusing those facts. Anyway, it's easy to confuse. So I'll go over an example of that and show you how to do that. Okay, so highest risk, again, in 60 plus individuals. People with comorbid conditions like heart, lung conditions. If you have, you know, diabetes is one of those things where it affects multiple systems simultaneously. And so that can be difficult to, you know, and that can lead to complications. Okay, so these definitions, you have a list of definitions, and I went over antibodies a little bit, but antibodies are what are created in order to protect against foreign attack, foreign substances that may be invading. So these antibodies are actually particles, and there's 5 antibodies, major antibodies in our body. IgG, IgM, IgA, IgD, IgE. Those are the 5, but it doesn't. I don't expect you to know it. I don't expect you to remember that. I just said it because for the sake of completion. Okay. So antibody blood test. That is where you are maybe not symptomatic. You might be one of those individuals that is thinking or hoping that you got it early, sometime in February. There's this whole group of people that hope that they had already been exposed. And so if you think you're one of those people, you can potentially get this test. Now this test is not very accurate. So you might want to get it, but again, it hasn't been developed that well yet. So asymptomatic, of course, I'm going to go over this so much that you'll get sick of hearing this from me. Of course, there's case investigators and case coordinators. So introducing a little concept of contact tracing. There might be, and it depends on the setup of where you work as a contact tracer. But this is not something that we're focusing on right now. So, okay. So this is all the things that I have already gone over. When it's on a surface, of course, a lot of times if you touch the surface and then touch your mouth or your nose or eyes, that's another way to get it, which is indirect. So that's there. I wanted to leave you also with, this was the original article. It's no longer new. There's a lot of cases, but in New York City, there was this, at that time, a pediatric multisystem inflammatory syndrome. It's actually called MISC. So the acronym is a little different than what I told you, but this is, the main thing from this is that children, people that say that children cannot be affected, not only are there situations where children have passed away, but secondarily, they might, initially they might have gotten the infection, they really didn't show much symptom, but secondarily 2, 3, 4 months down the line, they're getting this mysterious, sort of inflammation that's taking place. And the symptoms that you get from this is on the CDC website, but I wanted to highlight this, is the fact that it affects your heart, your eyes, your blood vessels, your skin. So we have seen this traditionally, and when they were actually characterizing this, they were calling this Kawasaki syndrome. This is something similar, but it's concerning. So school-age children can get something like this. Not only that, and this is new information, people that are children that are over the age of 10 can actually transmit the virus just as much as adults. So maybe they won't get it, but they can bring the virus back to their multi-generational home, and then make adults sick. So all of these things to keep in mind as the country is bracing itself to opening up schools. Okay, and then of course, the lives of teachers are also something we have to be concerned about. Okay. So these are, safety measures, social distancing, washing hands, 20 seconds. The time is important too, to keep in mind. And you'll have to excuse me, that's my granddaughter in the background. Okay, so, a lot of this is important. Social distancing, 6 feet, it's not 3 feet, it's not 2 feet. And when you're using, some sort of cleaner, make sure it is over 60% in alcohol content. Okay, so these are, of course, very important. And this is the original White House model, which was used. Of course, it was a group that was out of the University of Washington, very good group. I have worked with them in different projects and actually, published peer-reviewed journals. So it's a very reputable group. Initially, when the numbers were low, political leaders were adopting this model, but as soon as this model started to show deaths that were higher than what were desirable, other models were starting to be used. So this was the initial model. And if you haven't gotten a chance to look at that, you can take a look at this model. I think it's important to look at these curves. And with social distancing, without social distancing measures, they actually change the curves around to show you exactly how many lives are being saved by following these measures. So Chester asks makes a statement, with the asymptomatic persons, they don't show the symptoms at all, or the symptoms take a long time to show. Correct, yes, and that is a concerning segment, which I will be going over in detail on Thursday. So yeah, good point. Okay, so I was just trying to show off an article that I had about social distancing and social isolation. If you want to see some of the works that I have out there. Okay, so case fatality rate. I want to spend the last 5 minutes talking about this, or the last 2 or 3 minutes. So again, like I said, number of deaths over the number of cases. That's how, and then because it's a percentage, not a decimal, you have to multiply by 100 in order to get the right percentage. So here, this is New York as of May 14th. So this is when New York was kind of coming down from that peak that we all saw and were just tragically seeing, So what is the case fatality rate for Queens, New York? If you don't have to necessarily calculate this number, if you can just tell me what number over what number? So on the right, just to give you a little bit more, Queens is the second one down. The number is down there. So that's the deaths on the right. And on the left of your screen, the top number is the number of cases. Great. And so people are already calculating. And as you're calculating this and going over this, another important metric is the positivity rate. So that is proof that is used to refute, and positivity rates usually need to be less than 5%. And that is something that can be used to prove the fact that cases are actually going up and not going up because of the fact that there's more testing. Very important concept to understand. And if there are people that have this myth, that myth, then you can dispel that easily by saying that the positivity rate is increasing as well, so that then you know that there's a real increase in cases. So, and great. Okay. So I think for those of you that may be having difficulties, you can kind of ask me about that maybe first day in class on Thursday. But let me wrap up by saying, I'm really excited for each and every one of you to be a part of this. You've been attentive listeners. I see that there's a lot of interest. Thank you for participating and giving me all of those facts about COVID. It's a really great experience to be able to bring a whole group together and really discuss about this very important topic. As you go into Thursday, kind of you can look over some of the materials. There's a discussion post that you want to do do those, and then as you interact with others. There's also a place where you have for news, pieces that if you find interesting. If you find something interesting, share with the class. Everybody's interested in learning and finding out new information. And I think this will be a very productive class. Thanks for thanks for your attention and your time to this morning. And I look forward to seeing you again on Thursday.
Thank you.
Good day.
Thank you,
Yeah.
Dr. J.
Welcome.
Dr. B.
Yeah.